Welcome to this video tutorial on using the COMSOL modeling environment to visualize developing flow in the Cartesian coordinate system. One quick caveat up front, I recorded this using my personal version of COMSOL, which appears slightly different from the ClassKit license version available on machines at school. Please email me ASAP if you cannot figure out how to do something I did in this video in your version of COMSOL. After clicking on the model wizard, we're going to select our axis system. Selecting an axisymmetric system will create a model using cylindrical coordinates where one axis, r, has a fixed position at r equals 0, and COMSOL knows to integrate the theta direction around this axis in a circle. This video is focused on Cartesian coordinates, however, so we'll see how to do this in a different video. After choosing 2D as our system, we will see the list of physics modules we can choose from. The ClassKit license has significantly fewer of these, especially the turbulent models, but we will be modeling laminar flow here. To find it, expand the fluid flow line and then the single phase flow and select laminar flow with the code SPF in parentheses. Click Add and then Wait. Do not click it twice and the variables will pop up for this physics module. Note that COMSOL provides all three velocity directions, Vx, Vy, and Vz, even though we've told it we'll be modeling in only two directions, so Vz and the gradients in the z direction are all 0, unless we specify otherwise. Note that it's also defined the pressure, lowercase p, and the general velocity vector, u. Clicking Study brings us to the next screen where we can choose a steady state or time-dependent model. As we often do in chemical engineering, we'll just model the steady state solution, which should compile and solve much more quickly than a transient model. Clicking Done will create the model using these parameters and start us in the geometry mode of our primary component in the model. We will start by creating a rectangular area to represent a wide gap and then add a long, narrow rectangle to simulate this flow converging to a very narrow gap to observe the fluid velocities developing in that region. To do this visually, on the set of axes in the right-hand panel, first click on the Geometry tab in the toolbar and then click Rectangle. Now we can click anywhere on the graph to define one corner, and our second click will define the opposite corner. Let's make this rectangle centered around x equals 0 with a width of 2 meters and a height of 1 meter from y equals -1 to 0. This way our narrow channel can start up above from y equals 0 to all positive values of y. Use the red lines to line up your selection and double check it before you click to define the corner. If you mess up, you can always delete it and create another, or it might just be easier to make the corrections here in the input boxes for the dimensions and the location of the corner or center of the rectangle. Note that this has created a new object in the geometry section of the left-hand panel. We will see all of our objects and the operations we do to them appear here. Next, we'll make another rectangle, but first note that you can create a range of objects from this toolbar, including circles, ellipses, squares, and rectangles, both drawn from their corners or from their centers. And all these objects can have their values manually edited for more precise dimensioning. We're going to create another rectangle using corners and locate the bottom at -0.1 and 0, then put the top at +0.1 and 1. Note that the position of the cursor is also given by the black indicators on each axis x and y. Be sure to check your values for dimension and positioning to make sure you're drawing what you intended to. With both regions created, now we just have to tell COMSOL that these should be connected and made into one continuous region. The two different rectangles are shown in the left-hand side panel, but we need to add a Boolean operation to join them permanently. You can find this in the toolbar again, or simply by right-clicking the geometry in the left-hand panel. Make sure you keep these things in order though. The rectangles have to be created above the point where you add the Boolean operation to join them. We will select Union, and now that the Input Objects button is active, we can click on the rectangles to highlight them, adding them to the list of objects in this operation. If you've done this correctly, you should see both IDs, R1 and R2, listed in the Input Objects window now. We can go ahead and uncheck the Keep Interior Boundaries option to make this one contiguous region. Clicking Build All will show us the results. Now that we have a geometry, we would normally go on to define our material properties in the domain and boundary settings, but first we're going to back up a sec and create some parameters. To do this, you can right-click on the Global Definitions line at the top of the left-hand panel and choose Parameters to create this new line in the panel. Here we will define two values, V0, the inlet velocity, and P0, the outlet pressure. I probably shouldn't have given these the same subscript since they appear on opposite ends of the model, but this just goes to show that variable names are completely arbitrary. Note that when I define these values, I define their units in brackets, not parentheses or braces, but square brackets. COMSOL recognizes most SI units and some modifications like millimeters I'm using here. I'm actually going to come back and change this value to 0.0011 millimeters per second, but the outlet P will remain at 1 atm or 101.325 pascals. You can add descriptions to these parameters for later reference. Before choosing our material, we can jump to the initial values line in the physics section and enter these values as initial guesses for the entire domain. Since our inlet velocity from the bottom of our domain is v0 in the positive y direction, we will leave the initial value of 0 for u and enter v0 for v. This is in the positive y direction, so upward. After entering the initial guesses in the domain, we can go back up to the materials line of the left-hand panel and right-click on materials to add one. Or we can click on the materials toolbar and then on add material. This opens a new pane on the right hand side which contains several libraries of materials. I'm going to choose liquid water, which you can find in the materials library under simple oxides H2O. COMSOL will not simulate phase change data without you instructing it how to apply the thermodynamics and where the phase boundaries are, but it will calculate material properties that depend on the temperature. So it's important to note that we've specified the temperature in our system at 293.15 Kelvin or 20 degrees Celsius back in the domain settings. You should also note that there are several different entries for water which may have different physical properties. COMSOL is also used for things like sound engineering, so different materials have been added to the library for some specific purposes. Expanding the materials line in the left-hand panel, we can expand water to see the various functions defined for this library entry. Here we can see that the system will use the temperature-dependent expressions for density and dynamic viscosity, and if we examine the function, we will see that it is independent of pressure and any other system variables. When you are defining custom materials, you can insert analytical expressions for their physical properties in much the same way. Collapsing the materials line, we can move on to the physics section, starting with the fluids properties line. Here we can see the governing physics equations for this domain, continuity, and the Navier-Stokes equation, as well as the temperature settings and the source of physical property data required to solve the governing equations. You could change the temperature values here, for example, making it a T0 parameter, and then adding this variable to the parameters list with V0 and P0. But remember, the functions for these properties are only defined for temperatures between 273 and 373 Kelvin, give or take 0.15. And again, it will only simulate liquid water at this temperature. The next line, wall 1, is the default boundary setting for all boundaries not otherwise specified. Right now, this includes all boundaries in our system, and you can see that they are all listed in the selection box here. You cannot remove any boundaries from this list, but we can, however, define new boundary conditions which override this one for some, if not all, of the boundaries in our system. This is a no-slip boundary condition, though, so it suits everything in our system just fine, except for the inlet and the outlet. Under the Physics toolbar, click the pull-down menu for Boundaries and then select Inlet to create our first condition. Select the bottom boundary and make sure it appears in the selection window, and note that your boundary numbering may be different from mine if you built your geometry in a different way or a different order. Clicking on the Selection Active button will toggle it off, so I won't accidentally add any more boundaries to this list. Finally, we need to specify the inlet boundary as V0 because a normal velocity profile was selected. COMSOL will make sure the inlet velocity is perpendicular to the boundary, in this case pointed vertically upward everywhere. If we went forward with this inlet condition, however, we would see some weirdness at the corners of the inlet. This is because we just specified a perfectly flat profile, but we know that this fluid would actually demonstrate a parabolic profile, at least if it were fully developed. So we can specify the fully developed velocity profile for flow in a gap, at least for this wide section, 3/2 times the average velocity V0 times the expression 1 minus the quantity x over 1 meter, quantity squared. Note that if we left out the units, COMSOL would return an error that the equation doesn't work out dimensionally. Going back up to the default wall boundary condition, We can now see that our inlet boundary has been overridden with the new condition, and it will no longer be included in this no-slip list. Clicking on boundaries again up in the toolbar, we can now add the outlet condition. After selecting the top boundary, we can set the outlet pressure equal to P0. Again, we can click normal flow to make sure COMSOL not only suppresses any backflow or suction into the exit, but also assumes the flow is continuing on in this narrow gap, not suddenly expanding or contracting just downstream of this boundary. Returning once more to the default no-slip boundary condition, wall 1, we can see that it's now being overridden for both boundaries, which we defined alternatively, the inlet and the outlet. Now that we've defined our domain and boundary settings, we're almost ready to run, but first we're going to need to create our mesh. Remember that this type of modeling is based on finite elements, that is, COMSOL needs to first define all the points and domains where it will calculate average properties, like velocities and pressures, to balance the differential equations. Defining the default size mesh will yield very rough results in our narrow gap, so we're going to pull down the mesh menu and change normal to finer. When we click build all, we can see this new finer mesh. Remember that adding these extra mesh points will add extra time to our calculations, or rather to each iteration of our calculations, because the program has to define that many more values for each point. This is why I did not go past finer. I want this model to solve in a few seconds or minutes, not hours. After defining the mesh, we have everything we need to run this model and see if it converges to a solution. Opening the study toolbar at the top, we can find the compute button marked with an equal sign on the left-hand side. While it's running, COMSOL can show you the progress it's making toward converging to a solution. Above the graphics pane on the right, once one full iteration has been completed, COMSOL generates convergence plots where you can track its progress. Here we see a plot of the estimated numerical error in the model versus iteration number. If successful, COMSOL will take you directly to the first graphical results screen listed in the results section of the left-hand panel, but you can investigate the log of the iteration history in the panel below. The table tab will display interim results while the iterations are running, but the convergence plot is a plot of the data in the log tab. Clicking on graphics again, this default graphical results screen is a color map of total velocity, that is, the vector-based velocity magnitude. Note that the scale ranges up from a minimum velocity of exactly 0 because there is no negative magnitude of velocity. Expanding these default result plots of velocity and pressure, we can see the specific types of plots chosen for each. In the pressure results, we have a contour plot which is also color-coded, with red being high and blue being low pressure regions. Here we can see that the pressure drop through the narrow gap is very linear, equally spaced lines, and also nearly perfectly flat in the x direction. That is, the pressure in the narrow gap drops linearly with increasing y, and is not a function of x. This verifies the assumption that we make in the Navier-Stokes equation that dpdx is equal to 0. We can add additional plots over the top of this contour plot of pressure to visualize multiple things at once. Here we will add a streamline plot and select the bottom boundary, the inlet, as the origin of our streamlines. The default of 20 streamlines should be sufficient to see what's happening at the narrowing of the gap. Hitting plot will add the streamlines in black, tracing the path of the fluid through this laminar flow profile. Zooming in on the image and using the right mouse button to click and drag the plot to recenter it, we can see that the streamlines are all very densely concentrated parallel to one another through the narrow gap. And while this is very interesting, it's not telling us anything about how the flow is developed after entering the narrow gap region. For this, we need to return to the velocity profile. We can modify the range of velocities for which the color scale is applied to any color map plot, but first let's change the variable we're plotting here. Clicking on this pull-down menu, we can expand the laminar flow section to find all the variables, both inputs and results, available in the stored solution to our model. Clicking on velocity field, we can select the y-directed velocity v. Checking to make sure our expression is changed to v, and noting that we could change the units here if we wanted, we'll hit plot again to refresh. Notice that now our color scale is shifted to include slightly negative values, as there are some regions of this model where the fluid is flowing downward, if only slightly, in order to balance the differential equations for every finite element. After checking the manual color range box, we can grab the sliders and alter the scale of colors presented on the model. Anything outside of this range will appear as the same color as that end of the range, so lowering the max a tad and increasing the minimum will narrow the band of velocities we're looking at in order to better examine where the velocity is still changing. If we bump the max back up to the full range, we can see that the velocity on the center line of the gap appears to overshoot its steady state value just a little bit, then settle out to a constant value around 20 or 30 centimeters above the x-axis. Above that level, the velocity profile seems to be rather constant, aka fully developed. But to examine this effect more closely, we should really look at a more traditional plot, one of a type we could potentially ask you to identify or even draw in an exam question. In other words, a plot of velocity versus distance along a particular line. To do this in COMSOL, we're going to go up to the Results toolbar and click on Cut Line 2D. This will create a new cut line entry under the Derived Values section of the results on the left-hand panel. First, we'll look at the velocity profile across the throat of the entrance to the narrow gap region, so we'll define our cut line to be from negative 0.1 to positive 0.1 in x and at y values of 0 and 0. In fact, we'd like to look at a lot of cut lines at once if possible, and luckily COMSOL makes this pretty easy. Click on the Additional Parallel Lines button, and then on the Ruler button to the right, and you can define the start point, increment, and end point of y values for additional cut lines. Starting from 0, we'll increment every 5 centimeters up to a height of 30 centimeters above the entrance. Note that we could add an exponential or logarithmic function to this range to change the increment from the default linear scale. Clicking Plot again will show us our cut lines on the model geometry just to verify that they are in the right place. We're going to create a new 2D plot group to graph Vy versus our cut line length for all these cut lines. So after choosing 2D plot, change the dataset from study 1 to the cut line we just created, cut line 2D1. We need to add a plot to this result set, so go up and add a line graph and change the expression from default spf.u to just v, the y-directed velocity, and hit plot. Oh, there are way too many lines to make out what's going on here, so let's make this graph a bit easier to visualize by spreading these lines apart. We want to see how the flow is developing as it moves up in the y direction, so let's modify the expression to v plus 0.001 inverse seconds times y. This will slide our curves up more with increasing y values. Looking at this, it seems my guess of 0.001 spacing was a bit high, so let's lower that value to 0.0002 inverse seconds and hit plot again. Here we see that the velocity profile is definitely changing early on at the bottom. The first profile is relatively short and squat, bowed outward from a more flat profile in the middle where the parabolic behavior is not yet set in. It doesn't take long, however, for the profiles to decrease more on the outsides and squeeze the maximum velocity higher into the middle and then become perfectly parallel when they are fully developed. This is perhaps easier to see by rescaling the graphics pane to make the profiles narrower and steeper. But we can also look at the developing profiles in another way. If we define a new set of 2D cut lines that run along the y-axis in the direction of flow, we can observe the development more directly. Defining the set of vertical cut lines is a bit more complicated. Let's just say it boils down to the fact that the cross product of y across x is negative z instead of positive. So we'll have to define our first cut line where x is equal to negative 0.08 because the velocity at the walls, 0.1, is equal to 0. And then our increment will be negative 0.02 while the endpoint is negative 0.16. Again, because we don't need to hit the far wall to plot zeros. Now we can change our existing plots from the original set of cut lines to the new set, 2D cut line 2, and plot. Whoa, what happened here? Oh wait, that's right, we changed the expression to include a constant times y, which is now our x-axis, so we'd better fix that. Selecting line graph 1 in the left-hand panel, we can find the expression we added and delete it, leaving only the y-directed velocity. These graphs are naturally spread out because each one is measured at a different constant x value where the steady state velocity is different, ranging from 0 at the walls to the max velocity at the center line of the gap. This graph shows that the velocities are changing rapidly within the first 3 or 4 centimeters from the entrance to the narrow gap, some of them increasing and some of them decreasing, but around 5 or 6 centimeters in, they reach a local maximum or minimum where the velocities have overshot their steady state values slightly. This noise, some of it due to observable phenomena and some due to the granularity of our mesh of finite elements, steadies out by around 0.3 or 0.4 meters into the gap. Here we can say that the flow is fully developed and the velocity profiles are no longer changing in the y-axis in the direction of flow. One more thing we can do with this model is go and change the velocity value. Increasing the inlet velocity to 0.0021 millimeters per second, for example, will not only change the scale of the velocity profile, but also make them steeper, as their values near the entrance are closer to their values in the wider gap region than they were before. Bumping the inlet velocity up a bit further to 0.0051 millimeters per second will show this effect even more pronounced. Be careful increasing this velocity too much, however, as we can achieve turbulence pretty quickly in water. Change the material to air and delete water, and to be able to push this velocity up a bit further, while still using the laminar flow model in COMSOL. Another thing I wanted to mention in this video is the proper way to plot pressures. Because normal pressures will never be anywhere close to zero, even measured in bar, we should always modify pressure plots to graph gauge pressures, that is P minus P naught. This way, any positions having your base pressure P naught will be the lowest in the graph. With velocities, 0 is quite frequently the lowest value in any system, at least in magnitude. FYI, you can rotate 3D graphics by clicking and dragging with the left mouse button. The right button still pans so you can recenter. Don't forget to explore all the buttons above the graphics windows for more information and options for recentering, selecting things, etc. Finally, because we so carefully defined our inlet velocity as a parameter in the beginning, we can now take advantage of one of COMSOL's fancier features, a parametric sweep. Just like with the range of cut lines we defined, we can define a range of parameters for COMSOL to sweep and solve and store all at once. We're going to sweep the range of 0.0011 to 0.0091 with an increment of 0.001, defining the units as millimeters per second, just as we've been using all along. But before clicking compute, we're going to ask COMSOL to plot the results as it goes. And whoops, because these are all at different velocities, our line plots are all overlapping and differently scaled, so it doesn't make sense to look at them all at once. If we click on the plot group, we can change the parameter pull-down menu from all to from list, and we get to select which values of V0 we want to plot. Selecting the lowest value and clicking plot to refresh, we see the graph we had before, but holding control and clicking additional values, we can plot more than one at a time on the same axes. If I had rescaled this plot by changing the expression to V over V0, we would see overlapping plots for each of the cut lines along the sample positions in the gap. Lastly, you can create an animation to see how individual graphs change with the parameters. Click on Animation in the Results toolbar and choose Animation. Here we could export this to an MPEG or an animated GIF, but instead we're going to go back and choose the player option to view our movie in COMSOL directly. The default values all look okay, so we'll hit the play button and let the player compile the images. Uh-oh, it looks like the velocities are really low, but this is only because they're all scaled to the max velocity, which only occurs at the highest values of V0. So let's fix this by expanding the Advanced tab and unchecking the Synchronize Scales Between Frames box. Hitting the movie button again and waiting for it to compile, we finally see the true images with scaled velocities. Now when we hit play, we can see that the velocity profiles are getting steeper, pushing steadily deeper into the gap. The video will play on loop until you stop it or click to another screen.